Hello and welcome to my final project for winter term 2. So today I'm going to be talking about the least squares method. Now this is a mathematical method that's actually widely applicable not only to math, but I would say to real world examples, which is always lovely to see, especially in a high level math class. I hate to say it, but sometimes you do wonder, am I going to use this? But you're definitely going to see the real world implications of the least squares method of finding a line. So I've been doing problems where you get different data points and you have to find the best line of best fit between them, but I've always used my calculator, and now I come to find out it's actually really easy to just do it yourself. So I will be showing you how to do that. So the least squares method is actually really applicable to what we've been learning this term because it's a minimum maximum problem, which is kind of optimization, and it also incorporates directional derivatives, so it's really a double whammy, if you will. So let's talk about how applicable, or how we use it. So you do an experiment, you get a bunch of data points, and you can kind of plot them between the independent variable and the dependent variable. For example, here we have the height of tree forest with the number of bird species living there, and then on the right we have cigarette smoke per day versus percent with emphysema, and here we see the line of best fit already graphed. But that's basically what we're trying to do. We're trying to, in these experiments, these lines aren't, these data points aren't perfectly in line, but we can clearly see there's definitely a linear relationship between them all. So that's what we're trying to figure out, that linear relationship. This is the data we're given at first. The data points, x1, y1, x2, y2, however many you have, all the way up to xn, yn. Now, our goal is to find the line of best fit, which would be y equals ax plus b. But it's important to note right here that what we're looking for is a and b. It's not x and y, because what we're seeing here is, this is just our data points. I just wrote x1 and y1 just to show like they're constants. These are constants. A and B, that's the goal. That's what we're looking for. Okay, so now let's talk about how we're specifically in this case defining the best fit. So our goal here is to minimize the difference between the line and the data. And by that I mean, well, take a look at this just drawing I have here. So the stars represent the data points, and let's just say I'm going to sketch this, and let's say this is the line of best fit. What we want to do is minimize the distance between each point in the line of best fit, this pink line I'm drawing here. So we want to make that as small as possible, and that will determine how good the line fits. So we're going to create a function to measure how far each data point is from the line, and that's where the idea of least squares comes in, because we're going to measure the sums of the squares of these pink lines. And so the line of best fit, like I said, it's going to minimize the total square error or deviation, whatever you want to call it. So let's just review the equations. So first up we have this equation, and this basically is saying y and x at any given y and x. It could be x1, y1, xn, yn, but it's just like one of them, so that's where the xi comes in. Anyways, so y1 minus a times x1 plus b, or xi. What, you can see it right there. I don't know the terminology. But so this equation represents the deviation for each individual data point. So we plug in each star into the equation, and that's going to give the deviation for each data point. Now, we're going to so what I wrote here, this d function, is basically the function we're going to be using to calculate the least square, because d is basically the sum of all the data points of the squares of the deviation. So this is what we're going to be using. All we have to do is minimize d, and we get the least square. And we can calculate a and b using that. So that's what we're going to be doing from there. And make sure you can really look at this d function. Obviously the inputs are a and b, and you can kind of understand how it's just a summation of all of these squares of the deviations. Okay, so this is the equation where, this is the equation we are trying to minimize, right? So first I'm going to take the directional derivative from the a side, and we're going to set that equal to 0 because we do want it to be a critical point, aka minimized. So first off, we take the directional derivative. So now I've just expanded this here, and then simplified or rewrote this here. You might be confused why I chose this format, but you'll see in a second. By the way, we dropped the 2, you'll see why in a second as well. So now I've just expanded this one, the partial derivative with respect to b here, and then simplified or rewrote it here. Now, if you look at this format, you might actually be able to see the parallels from earlier. Remember before we had just this, what's in these parentheses here, y I minus a xi plus b. And you can shift that around to have y1 or yi equals this guy here. And you can really see the parallels here, because here we have a term of a. I don't know if term is the right word, forgive me, but you know what I'm trying to say. So here we have one with a, here we have one with b, here we have one with y, I, which is what we have here. And here we also have it. So this seems like we can pretty easily use these equations, even easier than this, to figure out what a and b will be for our specific data points in any given situation. And actually here we just get a 2 by 2 linear system, and we can just solve for a and b. So now let's try an example. So for this example, we're going to try to use the method of least squares to fit a line, to fit the best fitting line through the points 0, 0, which I'm going to graph here. Oh, sorry, I'm going to graph here. 1, 2, and 2, 1. So that's roughly what it should look like, and now let's figure out how to calculate it. So I just attached a picture of my work here because writing on Zoom is really hard. But let's remember, we want to make the linear line y equals ax plus b to best model the data. So the deviation of the data points for, xi, yi from the model is yi minus axi plus b. Now, by best, wait. Oh yeah. So by what we mean by best fit is, again, the minimizing the sum of the squares of the deviation. So rather than actually using what we calculated for on the previous slide, I'm just going to go back to step 1 so we can do it from there using the points, but obviously if you plug the points into what we calculated, it it could be even quicker and easier to solve this. So here we have our equation, and then I just basically plugged in the points because we have this summation guy, I forget what it's called. So it's saying we want all the points in this thing. So I did that and I added them. So here we have, 0, 0, 2, 1, and 1, 2. And then we take that down, and this is what we end up with. And we obviously it's in terms of b and a, which is what we're solving for, so that's perfect. And from there we can go right into derivatives. So here I took the partial derivative with respect to b, and as you can see, we went down calculating, and got 6a plus 6b equals 6. And then here I did the partial derivative with respect to a with this same equation up here, and got 10a plus 6b equals 8. Now, from there, what we're going to do is, so just continuing on here, I'm going to do some algebra. We can obviously set this 6a plus 6b equals 6. We can easily shift that into a equals 1 minus b over here on the left, and then we can plug that into this guy down here to get 10 minus 10b plus 6b, which we can 10b plus 6b, let's rewrite that as negative 4b equals 8. And then we just subtract 8 from this side, so we get 2, and then we can add 4b to the other side, so we get 2 equals 4b. Divide both sides by 4, and you get 1/2 equals b. Plug that back up top here, so we get 1 minus 1/2 equals 1/2. So a equals 1/2, and b equals 1/2. So we plug that into the equation that we're solving for, and the final line of best fit using the method of least squares is y equals 1/2 x plus 1/2. And obviously my graph is not perfect, but we can try to draw that line here and see if that makes sense. So our y-intercept 1/2, yeah, so the line's gonna look something like this. Obviously not perfect, but you get the idea. So as you can see, the method of least squares is actually really simple and widely applicable. Yeah, sorry if this was too long, and sorry if it wasn't complicated enough, but I did use the MIT link that was given in the topic ideas, and I thought that was really interesting. I spent a lot of time just kind of like dissecting that, and I feel like I really understand it, so yeah. So finally, here are all the sources that I referenced and learned the method of least squares from. So mostly MIT, thank you MIT. Okay. Peace and love. Oh, peace and love.